Okay, so the first law of thermodynamics, we introduced it earlier, but we're going to go over it in a little more detail. First law of thermodynamics says that the change in internal energy is equal to the heat added to the system minus the work done by the system. Now, again, when we talk about the work done by the system, we are talking about the work that the actual gas is doing. So the gas, the work that it does on the environment, it would be written like this. Sometimes you'll see it written, the first law, as Q plus W, okay? That would be the work done on the gas. So the two are basically talking about the same process. You know, one work is the work done by the gas. Sorry about the handwriting. The other one is done by the environment. Okay, conservation of energy. This is essentially a partially closed system. So the only way that energy can come in is through heat or through work. Okay. So again, first law of thermodynamics really isn't anything new. Again, we've applied it to a few different things, but it does allow us to relate the internal energy of the system to what's going on. And if it's an ideal gas, we can actually use a few other things to talk about how the energy changes. Now, again, here is a schematic diagram of what's going on. We can imagine that our system, this could be a cylinder, could be a gas turbine, it could be a number of things, a Stirling engine. We add heat to the system because the whole idea of thermodynamics is basically to turn thermal energy into work. We add heat to the system, and our expectation is that at least some of that thermal energy is going to be converted into work. We'll find out that it can never be 100%. But again, when we look at this, the change in internal energy is equal to Q minus W, the work done on the environment. Again, if we're doing the work done on the gas, we would add that. But for most circumstances, we're looking to get work out of the system. So this equation makes more sense. So looking at what we're trying to do, we are trying to create a device to extract work out of thermal energy. We call these systems heat engine. And we start with some source of energy, okay? The source of energy could be a boiler, okay? Of course, a boiler is going to have some external source of energy heating it up. It could be a nuclear reactor. It could be, oh gosh, you know, something, an internal combustion engine. The actual fuel-air mixture would be the source of energy there. But in any case, in this particular diagram, we don't really say what is producing the heat or where the heat is coming from, whether a chemical reaction is producing it, a nuclear reaction, or that it's coming from some other system that's giving up its internal energy. But we can see that this heat enters the heat engine, okay? Usually it transfers thermal energy. In many of our situations, we are dealing with an ideal gas. So when we heat an ideal gas, its pressure increases or its volume increases. This allows a piston to do work or a turbine to do work. We extract that work from the system, but we can never get 100% of that energy as pure work. We always get some dumped out of the system into another thing that we will call a cold reservoir. So as its name implies, a cold reservoir is at a lower temperature than the hot reservoir, and normally heat would flow naturally from the hot reservoir to the cold reservoir, but we put something in between it. We put a heat engine between the hot and cold reservoir. So we can extract some work from the system, okay? Very analogous to a water wheel, okay? We think about extracting energy from a hydro electric dam, or if you want to go back in time, an old water wheel at like a grist mill. Water would flow over a wheel, and the potential energy from the water would be transformed into kinetic energy and work for the wheel, and the wheel would turn a grindstone. In today, we have water that's coming from a higher elevation going to a lower elevation, and the potential energy there is converted into work. This drives a turbine, and the turbine, of course, generates electrical energy. If we think about this water wheel analogy, we can think about taking water from a higher elevation, okay, allowing it to flow over, somewhat a water wheel or some turbine, extracting work from it, and then allowing the water to go on its way and flow down the river, okay? So our heat engine is very much like this. The thermal energy comes from a source at a higher temperature. We allow the heat to flow into our heat engine. The heat engine does work, and then we exhaust this heat to the outside environment where the temperature is lower. So again, the analogy is water flowing from a higher elevation to a lower elevation. The water starts out with more potential energy and then ends up with less potential energy, all the while we can extract work from the system. Or in this thermal system, coming from a higher temperature with more thermal energy, flowing to a lower temperature region to be exhausted and extracting work in the process. So again, the first law of thermodynamics, if we look at it, is just energy conservation. We try to see where energy is flowing into the system. Usually it's in the form of heat, okay? But we can also do work on the gas. And then we look at where the energy is coming out of the system in the complete thermodynamic system, thermodynamic cycle. Heat comes in, work comes out. So again, for an ideal gas, this delta U just represents the thermal energy due to kinetic energy, microscopic kinetic energy of the molecules moving around. All right? In a real gas, this internal energy is all the microscopic energy. It can be the potential energy due to bonds. It can be the kinetic energy due to movement. It's just, general energy that the system has on a microscopic level, which we can extract to do work. Again, thinking about our first law of thermodynamics and our sign convention, when we talk about work, again, for the rest of the course, we're really talking about the work done by the gas. So if the gas expands, the work is positive. We can get mechanical energy out of the system as the cylinder expands, as the piston moves upward. If we add energy to the gas mechanically, we're compressing it, okay? In that case, energy is flowing into the system, the work is negative. Likewise, a convention for heat, if we add heat to the gas, Q is positive. If heat is taken from the gas, Q is negative. And this is important because to complete a thermodynamic cycle, we have to allow the gas to expand and be compressed. So generally, what we like to do to extract more work out than we put in is we like to have the gas expand when it's hot, okay? This way, it's going to be at a higher pressure. We're going to get more work out of the system, and we're going to compress it back when it's cold. Can't have that piston move, forever, so the gas can't expand forever. We've got to reset the system to complete the cycle. okay? And all the while, we want more heat coming in to the gas, okay, than we actually exhaust out into the environment. Because after all, work is the difference between the heat that flows in and the heat that flows out during one complete cycle. Finally, looking at delta U. Delta U represents the change in internal energy. For one cycle, delta U, because we're going to return to the original state, is going to be 0. So, we watch these thermodynamic processes. We'll see delta U go up as the gas gets hotter. We'll see delta U go down or become negative as the temperature drops. And this is just a summary of all the sign convention that we use. And again, this is the equation that we like. We like this one right here. We like delta U to be set up in such a way that as heat comes into the system, Q is positive. As we do work on the environment, W is positive. Again, I bring up the previous equation because sometimes you'll see it like this. This is the case, or this is written when, if heat is added, Q is positive. This is work done on the system. And I try to avoid writing the first law like this because it becomes confusing as to where the work is going. For this particular equation, this is work going into the system. We want the system to produce work. So this is the favored equation for what we use. Okay? Now, the change in internal energy of a monatomic ideal gas, all right? Monatomic ideal gas. And this is a pretty good approximation for things like helium, argon, neon, all the noble gases operate pretty close to monatomic ideal gases. Remember, with the ideal gas, we say that the molecules occupy no volume. So as long as we're not at a really high pressure or high density for these gases, we don't have to worry about that. Noble gases are notorious for having very little van der Waals forces between the molecules. So again, they behave much more closely to an ideal gas. Our first law looks something like this. And it's important to note that if we look at Q for this special case, and again, if it's not monatomic, it's not a monatomic gas, it's not going to act like this. This is the assumption that we're dealing with an ideal gas and not a real gas. Although it can be approximated well away from phase transitions, anywhere near a phase transition, this is not going to be a good representation. So we see that Q, and this is written in terms of molar heat capacity, Q is equal to the number of moles times the specific heat at constant pressure times the change in temperature, okay? If we look at this right here, we see that Cp is 5/2 R, okay? So Cp is the 5/2 and the R in there, okay? Monatomic gas again. The molar specific heat at constant volume is 3/2 R. We discussed earlier why Cp is larger than that. Your Cp is 5/2 R because at constant pressure, you are also doing work. So another way to write this equation for delta U, well, this is considering if no work is being done. Is this right here, where delta U represents, again, the change in internal energy of the system. Okay. All right. Now, suppose we have a system, monatomic gas, so we can use the CV equals 5/2 R. I'm sorry, CV equals, constant volume is 3/2 R. At CP equals 5/2 R. It has a pressure of 2 times 10 to the 5th pascals. It's isobaric, so it's just going to remain 2 times 10 to the 5th pascals. An initial temperature of 293 degrees Kelvin, and slowly expands at a constant pressure from 1 liter to 2.5 liters. Okay, just some important notes right here. This is what our expansion is going to look like. Okay, it's going to go from 1 liter to 2.5 liters along this straight line right here. So the work done is going to be the area underneath here, right there. Work's going to be pressure times delta V. All right. But it's also important to note that we initially start at 293 degrees Kelvin, right here. And if I were to draw an isotherm, it looks something like this. We are going to increase in temperature, hitting a new isotherm, again, at some final temperature, but I don't know what that is yet. All right. Now, let's do the first simple calculation that we can do for this particular case. What if we want to find out how much work is done? Now, as I said, isobaric, it's just going to be the area underneath the curve. It's really straightforward with this one. It's just pressure times delta V. We go from 1 liter to 2.5 liters. I could convert that to cubic meters. There's 1,000 liters in a cubic meter. So the conversion is 10 to the minus 3. So I go from 1 to 2.5. All right. I want to do final minus initial. So it's 2.5 minus 1. And that gives me 1.5 times 10 to the minus 3 cubic meters. And again, I just multiply that by the pressure. And the work done is 3 times 10 to the 2 joules, or simply 300. So 300 joules. Okay, that was easy. That is the work done there. Now again, this is an ideal gas, okay? Or we're treating this like an ideal gas, all right? We can therefore use the ideal gas law and the molar specific heat to find out some of the other things that are going on, okay? Let's find the change in internal energy of the gas. Now, as I said before, we are going to start at 293 degrees Kelvin here. When we get up here, we're at a higher temperature because, again, for an ideal gas, drawing the isotherms, I'm not going to be on the same isotherm. I'm going to be at a new temperature. I'm going to be at a higher temperature. And with the ideal gas law, I can determine what that new temperature is going to be. We know PV equals nRT. Now, in this case, the pressure is going to remain constant. So I'm going to group that off to the side with the other constants and bring the temperature over to the left-hand side. I'll divide both sides by T. I'll get rid of the T over here. And I'm going to divide both sides by P. Okay, that'll get rid of the pressure over here. And my new equation says V over T equals NR over, oops, I did this wrong. I'm drawing this wrong, okay? P doesn't cancel out on that side. P cancels out on this side. Good. So NR over P, this is a constant, so V over T doesn't change. What that means here is that my final volume over my final temperature is going to be equal to my initial volume over my initial temperature. Okay? So if I want to solve for my final temperature, I can put that off to the left-hand side of the equation by itself. All right? Now, if you cross multiply this, and then you divide both sides by VI, I'm not going to go through all the algebra. You can get this equation right here. Okay? So, once again, I need to find the new temperature. I was at 293 Kelvin, but we know in an isobaric expansion, the pressure to remain constant means it's going to have to be at a higher temperature. I'm going to try to find this final temperature over here. So I plug in all my different values. I start at 293 degrees Kelvin. My final volume is 2.5 times 10 to the minus 3. My initial volume was 1 times 10 to the minus 3. So my new temperature is going to be 733 degrees Kelvin. Okay? Now, the other question is, given my temperature, what do I need to calculate my internal energy? I needed the temperature change. That's very important. But remember, the change in internal energy is not only related to what the temperature is doing, it's also related to the number of moles. The more moles you have undergoing a temperature change, the more energy it's going to take. So I need to calculate how many moles of gas I have. So I can do this pretty easily using my initial point or using my final point. Again, ideal gas PV equals nRT. So N, I can solve by itself. Divide both sides by RT. Okay, and that gives me this expression right here. I'll use the initial point. Pressure is constant. The initial volume was 1 liter. There's my gas constant. There's my initial temperature. And this will work for the initial or the final point. If I put in the final temperature and the final pressure, I would have gotten the same thing. So I have 8.21 times 10 to the minus 2 moles. Okay? So, very important here. I have the temperature and the number of moles. R is a constant. I know my pressure. I know my volume. Now I can solve for all the other unknowns. Okay, so here's our equation for the change in internal energy for a monatomic gas. 3/2 nR delta T. Okay? So just plug in everything. There's my number of moles, N. There's my gas constant. Remember, I go from 293 degrees Kelvin to, what was that final? I'm going to have to cheat. Oh, 733. To 733 K. Okay, so that's a delta of 440. Okay, and that tells me that my internal energy is changed by 450 joules. Now, this is interesting. Think about where we are at this point. We said the work done by the gas on the outside is 300 joules. The change in internal energy is 450 joules. Okay? Now, by the first law, delta U is equal to Q minus W. So delta U went up by 450, even though the system lost 300 joules as it did work on the outside. So what does that tell you about Q? Okay, Q must be the sum of these two. We had to add heat to the system so it could do 300 joules of work and still gain 450 joules of energy. So once again, we'll use that first law of thermodynamics. We've already said delta U was equal to this. We already said that we did 320 joules. I'm sorry, 300 joules of work. Okay. So that gives us the total heat put into the system. Again, if you write this out, solving for Q, we add work to both sides. Okay, so this should be a plus right here. Plus, okay, don't know why I wrote it like that. But basically, oops, that would be gone. Basically, I had to add heat to this for two reasons. I was losing energy from the system as it was doing work on the outside, filling in this area right here. But again, we were also going from a lower temperature, okay, and increased by 440 degrees Kelvin to a higher temperature, okay? So in an isobaric process, we require a very large heat input to maintain the pressure, because as the gas density is going down, we need more temperature to support that higher pressure level. Okay, this is sort of an aside. It's not a direct application of the first law of thermodynamics, but in many ways, we can look at human metabolism, where we're changing the internal energy of a system as being equal to heat minus the work done. Obviously, we're always generating heat, so that's always going to the outside. And of course, our muscles are doing work, so we can lose energy that way. So, thinking about what's going on here, as homeotherms, we are dumping heat to the outside. So technically, that would be heat leaving the system. So we have to take in food energy in order to maintain that loss. And also, if we're doing work through our muscles, that energy is going to be lost too. Okay, so one thing that we can talk about in terms of how energy changes in our system is looking at the rate at which energy is being used. Okay, so this metabolic rate is written as how our internal energy is changing as a function of time with respect to energy being used. All right, this is directly proportional to all the different chemical reactions that are going on, which all depend on oxygen. So here's an interesting relationship between the power, and again, look at this. This is energy divided by time. So that's power. Okay. The rate at which we use energy is equal to 4.8 times, and this is, we'll see the units that are used here, 4.8 times the volume of oxygen taken in per rate of time. Okay, so if we look at the general amount of power that we use, our bodies are normally using about 80 watts just to maintain the very basic functions of our body. That's basal metabolic rate. Okay, You need to take in so much oxygen, otherwise you stop living because you can't maintain this metabolic rate just to keep the organs functioning. But if you do more work, obviously your metabolic rate is going to have to go up, okay? Now, here are some different metabolic rates. This is for a 65 kilogram male. This is not great, but it just gives you an example. Not everybody's a 65 kilogram male. So you really should adjust this to your metabolic rate as a function of your body mass. So normally we talk about, and it's more useful to talk about metabolic rate, delta U over delta T, per kilogram, per mass. Okay, that's a much more useful way to talk about, because so it sort of equalizes for different body sizes. So looking at this again, here's our basal metabolic rate. If you're sleeping, you're not going to use much more than 80 watts, per 65 kilograms of body mass. Oh gosh, I can't do that quickly in my head, but roughly about, what is that? About 1.3 watts per kilogram of body mass. Now, obviously, as we increase our activity, the metabolic rate increases. Just light activity, you would be burning about 230 joules per second. Moderate activity, 465 joules per second. Heavy activity, 700 joules per second. And we're going to look at the peak metabolic rate for different people. And if you're really generating a tremendous amount of power, up around 1600 watts, would be our metabolic rate. Now, it's important to note that, again, this is going to be different for different body sizes, but we can actually talk about what is, now we're switching, we're switching units here. Again, here we're connecting, let's do this. On this chart, we're going to connect metabolic rate with oxygen used, okay? And that goes back to that original equation. And unfortunately now, they've switched here. This is now milliliters of oxygen per minute per kilogram. It's not a very useful way of looking at this. But, obviously with a 65 kilogram male, if we multiply this 3.5 times 65, that would give us how much oxygen we'd use per minute. At 10 milliliters per minute per degree per kilogram, a 65 kilogram male would be using 650 milliliters of oxygen every minute that went by. Okay, but let's go to this right here. Again, I'm not real happy with the crazy units that they're having here. Milliliters per minute per kilogram, but that's the table that we're stuck with. You've probably seen pictures or videos of athletes on a treadmill hooked up to a respiration device. Not a respirator, but a device that measures the amount of oxygen flow. They've got this oxygen mask on and they're running on the treadmill. What they're trying to do there while they're on the treadmill is measure the amount of oxygen they consume at peak aerobic performance. Okay. Now you can actually, generate more power for a short amount of time. If you're sprinting or you're doing a lot of heavy lifting, where you use your type 2 muscles, and you're basically using the creatine phosphate in the muscles and the glycogen in the muscles, but that has to be paid back. To really measure how efficient one's cardiovascular system is, you've got to put somebody on a treadmill and just push them and see how much oxygen they can consume. So the more fit you are, the more oxygen you can take in. So let's say somebody was in very poor physical fitness. They would only be able to consume 28 milliliters per minute kilogram. Okay? Now think about this. Very poor fitness could be due to a number of factors. Somebody might be ill, which would inhibit how much oxygen that their lungs could take up. So certainly somebody with pneumonia would have difficulty here. Somebody with COPD would have problems actually taking in the oxygen. And then on the other hand, if we think about the oxygen being delivered to the bloodstream, if the heart is compromised, that would also make it very difficult to get the oxygen to different parts of the body. As fitness level goes up, our ability to take the oxygen in and deliver it also increases. Poor physical fitness would be about 34 milliliters per minute kilogram. Average or fair, 42. Good, 52. And then excellent would be 70 milliliters of oxygen can be taken in per minute kilogram. Okay, kilogram of body mass. And again, this factors out anaerobic activity, because again, anaerobic activity is really a loan that your body pays back. You burn up the creatine phosphate, you burn up the oxygen while generating an oxygen debt. Here, we're using the oxygen directly from the cardiovascular system. So on the treadmill, they're actually measuring this over a prolonged period of time, more than the minute it takes to use up all the glycogen. I think the creatine phosphate's used up in 10 minutes. So again, looking at metabolic rate, again, this is for somebody at a particular mass. Here's looking at the metabolic rate for different activities. Okay. Here is the physical power output. Okay. So when we connect one number to the other, cycling would be highly aerobic. Okay. And we can see there, we put out 96 watts of power for a power input of 505 watts. Okay. So if we do useful work divided by energy input, that gives us an efficiency of about 20%. That's about the best that the human body can do. 20% mechanical efficiency for the input. Okay. And it gets worse for anaerobic. Once you go to anaerobic, like shoveling snow, here you may only get about 17.5 watts of power out for a power input of 570 watts. And here we see an efficiency of only 3%. In fact, you can drop it down 0%. If you're doing isometrics where your muscles are actually not moving, but yet burning energy, you're not getting any work out.